I'm delighted to be here today, and I wanted to start out with a roadmap of what we will be presenting. So I'm going to give some preliminaries to sort of orient everybody so we're all on the same page. An introduction, we'll talk about, what is evidence and how do we think of evidence in order to make causal inference. And then Jose is going to take the bulk of the technical work. He's going to go through potential outcomes, randomization, and matching methods. And then a very detailed example on the impact of a natural disaster on educational outcomes in Chile. And then I'll conclude with some practical considerations. In terms of preliminaries, what are our goals today? Well, first of all, it's to provide a conceptual basis of cause and effects. And it may sound very simple, but we want to be very precise. We're going to lay out some of the causal assumptions, and hence that those are the assumptions that you should be familiar with by the time you leave this tutorial. And then to understand the strengths and limitations of various approaches to causal inference. Our setting today is going to focus on binary treatments, and sometimes we'll call them treatments, sometimes we'll call them interventions, sometimes we'll call them exposures. But it's going to be treatment comparators, so just two choices. We're only going to look at a single primary outcome. We know that in many studies there are multiple outcomes that people want to infer causal inference, about which people want to infer causal inference, but we're just the one primary outcome. We're going to talk about a single sharp hypothesis tests, and we're going to focus on matching methods. And Jose will go through those, but there are many other methods that fit in nicely in this framework, but we're just going to focus because of time today on matching methods. And finally, we're going to, we want to make inference. The tutorial is causal inference, so what's the inference part? And there are many approaches to making inference. We are going to focus on a randomization-based inference. And so to contrast that, there's sort of the superpopulation focus on inference where you sample some population and then you get patients and you end up getting an estimate of a treatment where, again, you take in the sampling variability of that population. The randomization-based approach is really going to focus on the sample of patients you have at hand. So the sample's fixed, and how do we make inferences? And again, going forward, that will be clear, but we wanted to make sure that you understand there are lots of different frameworks for thinking about causal inference. I also wanted to highlight some of the work that has been accomplished by Harvard faculty. And so what I've done is I've produced just a sample of books. And so the faculty come from the various schools, the Faculty of Arts and Science, the School of Public Health, and the medical school. You may not be able to read this exactly, but we have all of these books are about causal inference, different perspectives. I will note I could not find the real face cover of this book. So it's a template. That's not what the book looks like. If you want to look for a brown book, it's random if it ends up being brown. But Miguel Hernan and Jamie Robbins. So again, there are many more people here at Harvard University that do causal inference across all the schools. And so I just wanted to highlight that fact for you. And then I do want to acknowledge support for work on causal inference. This is a grant, actually, Francesca's also on the grant from the National Institutes of General Medical Sciences. And Jose's work has been partly supported by a grant from the Sloan Foundation. So before I get to the introduction of the tutorial, I do want to say that if you have questions, we welcome them, so please ask them. If we find that we're too short on time, we may say, let's defer it and talk about it later. The problem I will have, I don't know if Jose will have that, is I don't know if I'll see you. So if you're asking a question and make a lot of noise if I can't see you, ask a question. Okay, so I'm really going to talk about what do we mean by causal inference, and what do we mean by evidence for causal inference. So some of the examples that cut across a variety of areas are the following. So I work in the medical area in health services research, and some important questions are whether or not your health insurer should cover the costs of new procedures, new drugs that are approved by the FDA. And so one particular example are, do drug-coated balloons reduce restenosis rates among Medicare beneficiaries with a particular disease? So there we have a treatment. It's a drug-coated balloon, and basically that just is a drug, and it squishes away the plaque in your arteries, versus it could be a non-drug-coated balloon. The outcome here is restenosis, and we're looking at a disease-based population. I also do work in transportation, and in that area, you could think of safety. And so one question that may be asked is, does low pavement marking visibility cause nighttime crashes? So when you're driving on the road and you're thinking, where's the line? Is that actually causing nighttime crashes? Versus if you have clear visibility of those more marked pavement markings. So again, a causal question. Trademark infringement. So you could, in the case of the law, if you're going to say there is infringement, what you need to show is whether or not a good or service causes confusion regarding the source of the good or service. And so there it's, you want to know whether or not the good or service compared to not that good or service is actually causing confusion. And another example is in geophysics. I don't know anything about this, but an example would be, does planetary wave activity in the lower atmosphere cause ionospheric total electron content changes? So this is really meant to say, or to demonstrate, causal questions exist in many fields. In some fields, they're harder than others. We'll get to this later on in the talk, but if you want to think about replication, I don't know how we can replicate a planetary wave activity, but again, there are things you can think about to put your mind in the causal inference setting. So what is evidence? And again, evidence takes many forms and shapes, but I think an important point to emphasize here is an accumulation of information. So you'll get evidence from some studies, but you're going to get, in order for it to be real evidence, you want lots of confirming pieces of information to refute or support a particular theory. We want to ask whether or not the finding can be replicated, and hence that's why we want to look in different study designs, different settings, maybe in different populations. Do we find the same finding? And then the other question for evidence is, you should really think about, is there an underlying mechanism? So we're contrasting this, of course, with predictive inference. We can predict things using all sorts of information. It may not make sense to us, but we're fine if we have a predictive inference. We're predicting well. But in causal inference, you really do want to think about, why is X causing Y? And so that's the underlying mechanism. In medicine, there is a hierarchy of evidence. And so this is actually a pyramid where at the bottom you have in vitro test tube research. And as you go higher and higher, you get to controlled studies, randomized designs, and then many randomized designs. So again, one may think that the quality of evidence is different, but it really depends how well the study's been done. So the point here is many types of studies contribute to evidence, whether or not they're observational, whether they're randomized, whether they're looking in animals, but you want to make an inference about human beings. All of that is evidence, and we need to think about that and understand that if we want to make causal inference. So certainly in public health, we always go back to Bradford Hill in 1965, wrote a paper that many epidemiologists would refer to in terms of what he described as evidence needed if you're thinking about a cause and effect. And so these 9 items were written in 1965. They still apply today. You want to look at how strongly the cause is related to the effect. You want it to be consistent. You want it to be specific. Is there, if it's a dose response, if you give more of the drug, do you see more of the effect? So again, there's a gradient there, whether it's plausible, where it's coherent, by analogy. And here I've bolded experiment because that's what's going to be our thinking today, experimental thinking. We are going to set up the framework of creating evidence with the thought in mind of conducting an experiment where you have control of the treatment assignment, the intervention assignment, whatever, in your hands. I also wanted to say that for people that were at the conference yesterday, there was discussions about big data and algorithms. So computational algorithms in massive data sets. So we just want to emphasize that clearly these opportunities can help the way we conduct observational studies, but we're not going to talk about any specific considerations with big data. So we're not going to talk about machine learning in this workshop. It really is a side question. It's an important side question, but we're going to focus on the fundamentals. So we know that the amount of data is growing at a staggering pace. And finally, we do want to emphasize, and that will be the lesson basically for today's tutorial, is that predictors are not founded on causal relationships, and the use of big data is not a substitute for thoughtful study design. And so we're going to be focusing on thoughtful study design today, and that will be the emphasis. So now I'm going to turn it over to Jose, who's going to go through the bulk of the presentation and this tutorial to talk about causal thinking.
Thank you very much, Sharon-Lise. Yes, we want to do a careful study design and carefully talk about causal effects, and for that we need to introduce the right notation. So I'm going to start by introducing the potential outcome framework for causal inference. Suppose that we want to estimate the effect of a labor training program on a given person I. We're going to have this running example throughout the most of the presentation. Again, this example about the impact of a labor training program, ideally on a single person, but as it turns out, we'll have to do it for a sample of people, as I'll explain in a minute. We're going to define this notation, the potential outcomes notation, which we're going to say that for each unit I in the sample, we're going to have the outcome that this person would have shown under treatment and the outcome that this person would have shown under control as yi1 and yi0. So in our example, we can think that this outcome is earnings after the labor training program. yi1 would be the earnings that this person would have shown if treated, otherwise if control. The problem, of course, is that we get to see only one of these states of the world. We only get to see the outcome of the person if the person underwent treatment or if it underwent control. We never get to see the two of them. And this is what is called the fundamental problem of causal inference. We would like to estimate this contrast, this difference between the outcome that the person would have shown under treatment minus the outcome that the person would have shown under control here. But as said, we never get to see the two of them. These individual effects are cannot be seen in the data. They're not estimable. So we cannot get to estimate this quantity that we wish we would estimate. So here I wish to emphasize that a causal effect is defined as a contrast between two competing treatments, between two well-defined alternatives. When we talk about an effect, we want to be very clear not about only what is the treatment, but what is the alternative to treatment, the control. In this case here, treatment is undergoing the labor training program, and control is not being part of the problem. And this is important because in some cases the alternative is not all that well defined. For example, when we ask what is the impact of obesity, what do we mean exactly by obesity and by not being obese is not that clear. So this is something really important. In this presentation, we're going to be focusing on this difference in potential outcomes, to be precise, in a sample of units, but I wish to emphasize that we could have also focused on this other contrast, which is the ratio of potential outcomes. So this is what we would like to estimate, but we can't because we get to see only one realization of the world. People are treated or they're controlled. We don't get to see both states of the world. Otherwise, causal inference would be quite easy. In an ideal world, we would see something that looks like this. We would be this omniscient researcher. We would get to see this science table, as Don Rubin called it, where for each unit here I'm highlighting the first unit in the sample of 10 units that we have. This is the income that person 1 would show under control. This is the one that it would show under treatment. This person actually underwent control. And under control, the outcome that we get to see is the potential outcome under control. And the individual effects are simply these differences. So if we were to be this omniscient statistician that gets to see everything, the problem would be quite easy. The problem is that in practice, in real life, we're dealing with a table like this one, which we can call the statistician's table, where under control, we get to see the potential outcome under control, as we're showing here. We never get to see the potential outcome under treatment, and this difference is not identifiable from the data. All right? So what can we do? We start asking the question about an individual effect. We cannot do that unless we put a lot of structure on the problem, unless we make some very strong assumptions. So what we're going to do instead is, instead of asking the question for an individual unit, we're going to ask, can I estimate an average effect? Can I estimate an average effect unbiasedly? So we're going to settle for an average effect, namely a sample average treatment effect on the treated. That is going to be our estimate here. And for that, it turns out that we can do something. The statistical solution to this fundamental problem of causal inference is to settle for this average effect and randomly assign subjects to treatment and control. Because by randomly assigning subjects to treatment and control, this sample of treated subjects is going to be, if you wish, representative of the sample of controlled subjects, and both are going to be representative over the overall sample of subjects. So you can unbiasedly estimate the effect of treatment by taking the average of the outcomes here and the average of the outcomes under control, the difference between the two. Another way to think about this is that randomization is going to produce two groups that are balanced, that they're equal in expectation. Randomization is going to make sure that these two groups are similar in terms of observed and unobserved covariates. Here I'm showing you an example of a block pair randomized experiment where we're randomizing within pairs. I'm choosing this structure to prepare the ground for talking about matching afterwards, but it's also a good idea to randomize within blocks to ensure better balance at the end of the day. So randomization, it biases these two groups that are similar in expectation in terms of things that we can see and things that we cannot see. Hence, differences in the outcomes at the day we can attribute to differences in the treatment as opposed to differences in confounding variables. So that's the statistical solution to this problem of causal inference, randomization. Let me introduce the notation more carefully. Throughout this presentation, ZI is going to be this treatment indicator, which is going to be 1 if person I is assigned to the labor training program and 0 otherwise. And we're going to distinguish again between the observed outcomes and the potential outcomes. So if z equals 1 here, we get to see this is the observed outcome. We get to see the potential outcome under treatment. If z equals 0, we get to see the potential outcomes under control. We're also going to have a vector of observed covariates, and ui is going to be an unobserved covariate. In this framework here, everything is going to be fixed except on treatment assignment, z, and the variables that inherit the randomness from treatment assignment. So the observed outcomes are going to be thought as fixed, but the potential outcomes, the observed outcomes are going to be random because they inherit the randomness of treatment assignment, but both the potential outcomes and the vector of observed covariates and unobserved covariate, they're going to be thought as fixed. So randomness here is coming from the randomization distribution of treatment assignment. All right? And we wish to estimate the sample average treatment effect on the treated. I wish to highlight that this notation is super important. It avoids us to make many mistakes, as I'll say in a second. But embedded in this notation, there's this very important assumption called the Sattva Assumption. The Sattva Assumption stands for Stable Unit Treatment Value Assumption. And it has two assumptions within this assumption. First, this assumption says there's no interference between our units. And second, it says there are no versions of the treatment beyond those encoded by Z. To give you an example, the meaning of there being no interference between units says that participation of one subject in the program does not affect the outcome of another subject. Okay. This is an assumption that is violated in some settings, for example, in vaccine trials. If one subject gets a vaccination, that is likely going to affect the outcome of another subject, right? Because of contagion. So we're ruling out this in this notation, but there are generalizations of this notation to take care of that problem too. And second, we're saying there are no versions of the treatment beyond those encoded by Z. This means that there are no levels of labor training. A person is part of the labor training program or not. It's not that you get a little or more of labor training. You can also extend this notation to doses. All right? But I wish to be very clear that the notation here is implicitly saying this. If we want to think about multi-value treatments, then we have to extend the notation. This is for binary treatments. And I think this notation for causal inference is a triumph because it allows us to think carefully about causal inference and separate the quantities that we wish to estimate from the models and estimators that we use to estimate those quantities. The potential outcomes framework was developed by Niemann and Rubin, and Holland has a very nice paper discussing this potential outcome framework. Robbins and Hernan have extended this framework to longitudinal studies, and Imbens and Woolrich, in a very nice econometrics survey paper, they discuss the advantages of this potential outcomes framework. And again, what they say is that this framework allows us to decouple the quantities that we wish to estimate, to then say under what assumptions we can actually estimate those quantities from the data without making any parametric assumptions about the methods. Those come later. The alternative approach, which we can call the estimators first approach, poses a model and then asks the question, okay, under what assumptions is this really a causal effect? And oftentimes we run into trouble by doing that, and we end up imposing very strong assumptions that we don't want to impose. So I think it's quite handy, this notation, to talk about causal inference, again, because we start by defining the quantities we wish to estimate, then we talk about assumptions, identification, estimators, and so on. I'll explain more this in a second. But there's also some criticism about this potential outcome framework, and here I would refer you to this paper by David in JASA with a discussion. So this is the mostly used framework, but there are also other views that you should know about. So randomization is the statistical solution to the fundamental problem of causal inference. Let me explain you more carefully why is that. We said that in a randomized experiment, the treatment groups tend to be similar in terms of their observed and unobserved covariates, such that at the end of the day, we have this nice table 1 for covariates, where we see that the treatment and the control groups are similar in terms of their means, but we also expect the distributions of these covariates to be the same across treatment groups. Hence, differences in outcomes can be safely explained by difference in treatment as opposed to confounding variables that we can see. But most importantly, randomization also buys us balance in terms of things that we cannot see. So randomized experiments are the gold standard for causal inference, the most reliable approach for learning about the effects of treatments, because randomization biases an unbiased estimator by construction. And second, I wish to emphasize too, because randomization gives us a basis for inference without resorting to any kind of assumptions. This is what Fisher called the reasoned basis for inference. And I want to explain these two things, particularly the second one, because it's going to be our model for inference, which is going to be valuable later when we move to observational studies and ask the question about a hidden covariate. To what extent a hidden covariate can explain our significant findings. So this is why I wish to spend some time explaining this second role of randomization, because it will facilitate a mode of sensitivity analysis to hidden bias, which is really important in observational studies. All right? But first, let me talk about the role of randomization for statistical control. Using Fields-Davis notation for independence, randomization guarantees that the treatment assignment is independent of the potential outcomes under treatment and under control. In English, this is saying that the flip of a fair coin knows nothing about ourselves. The flip of a fair coin knows nothing about how my outcomes would show under treatment and under control. It cannot predict it. The distributions of these two potential outcomes are going to be the same across treatment groups, and therefore the means are going to be the same, and so on. This is something that we get in randomized experiments by construction, because we're randomly assigning subjects to treatment and control. Because of this, we can estimate the average treatment effect on the treated from the observed data. This is the quantity that we wish to estimate, the average treatment effect on the treated. To be precise, it's the sample average treatment effect on the treated, so these expectations are going to be taken over the distribution of the random assignment. That requires some careful definition, but it can surely be done. I just wish to emphasize that because of independence, you can get to see this from the observed data. So because of linearity of expectations, you can write this as the difference in means, right? The expectation is a linear operator. And because of independence, I can switch this indicator, because since Z is random, the distribution of the potential outcomes under treatment and under control is the same in both groups, and hence the mean is the same. So this is what independence buys us. And then if I'm working with the treated subjects, I get to see the potential outcome under treatment. So because of this coherence of potential outcomes and the observed outcomes, I can change this for the observed data. The point being that we have written the quantity we wish to estimate in terms of these potential outcomes very well defined, you know, and then under this assumption that we have by designing randomized experiment, we can identify this, we can compute this from the observed data. For example, by taking the difference in means, in sample means, between the treatment and control group. All right? And similarly, we have that in a randomized experiment, the ATT, average treatment on the treated, is equal to the average treatment effect over the overall sample. Because of that assumption over there. In the same way that we could change these indexes here, these indicators, we can get rid of them. All right? So that's the role of randomization for statistical control. But there's this other role of randomization often overlooked, which is really important for inference. And again, it's going to facilitate a sensitivity analysis to hidden bias. And the point is that randomization, by this physical act of flipping coins like this, you're physically inducing a distribution that can be used for exact testing. What's the meaning of that? That we're going to compute p-values by counting, as opposed to resorting to distributional assumptions from the start. We're going to be doing these non-parametric tests, which I think is helpful, particularly in smaller samples. So we're going to consider this null hypothesis, this Fisher null hypothesis, also called the sharp null hypothesis, which says there's no effect. And no effect means no effect, period. No effect on anybody. For all I, there's no effect. This is the first question we're going to ask to the data. I think it's the first question we can ever ask to the data. A second question we can ask to the data is the question about a typical effect, where the average is 0. That is also a very good question. That's the Niemann null hypothesis. But we're going to start from here. You can also do randomization-based inference for the Neymannian null for the average. But I'm going to start from here to fix ideas. All right? So no effect means no effect. What is the testing procedure here? Well, the recipe goes as follows. First, we're going to assume that H naught, the null hypothesis, holds. If it holds, if there's no effect, the observed outcomes are fixed, right? If you're treated, I'm going to see the same outcome than if you're controlled, right? Treatment is doing nothing. Second, we're going to consider all the possible set of random assignments, omega. Okay, I can randomly assign pairs in 2 to the number of pair ways, right? Third, we're going to choose a test statistic wisely. We're going to compute the test statistic, and then we're going to calculate how often I see a value of the test statistic that is at least as extreme as the observed one under the null hypothesis. Don Rubin has a very nice way of thinking about hypothesis tests and the sharp null, which is, he says, a stochastic proof by contradiction. In a proof by contradiction, we start assuming something, we push through the logic of that something, and if we end to something that is nonsense, then we reject that initial hypothesis. This is the same thing here, but there's randomness here. So we're going to assume this holds, we're going to push through that logic, and then we're going to ask, okay, how likely is it to observe a value of the test statistic at least this extreme? It is very unlikely. We're going to reject the null hypothesis. That is the logic of hypothesis testing. And we're going to do this by counting here. And this example considers matched pairs and is taken from this book by Paul Rosenbaum on design of observational studies. We're going to have this matched pair design where we're randomly assigning subjects to treatment and control by flipping a coin, by flipping a fair coin. One possible treatment assignment is this one here, but another one would be to have this lady over here be in the treatment group, like here. I have just switched them, if you can see them. Okay? Another possible assignment is to switch these two gentlemen's, right? The flip of the fair coin could have been that one, and so on. We have 2 to the 5, in this case 32 possible treatment assignments. These 2 to the 5 possible treatment assignments can be listed like this, right? In the first row, we have that the first subject in every pair is assigned to treatment. In the last row, the last subject in the pair is assigned to control. It's the opposite. But we have this pair design in which we have matched before randomization subjects on their age, on their race, and then we have randomly assigned them to treatment, and then we get to see this outcome under treatment for the first subject in the first pair, and this outcome under control for the second subject in the first pair, and here we can write the difference between these outcomes, right? Under all these possible treatment assignments here, I'm highlighting in green different possible assignments. I can compute that difference in pairs, right? Remember that randomization is doing nothing but flipping the sign of people. So if you two are matched, and if you're treated and you're control, if your outcome is larger than yours, I get to see a positive difference under this assignment. But if under another pair, another possible assignment, I get to see the same absolute difference, but with a but with a negative value, and so on. So in our experiment, say we get to see this difference in outcomes in pairs, and taking the mean difference of all these differences, this is the value of our test statistic. This is not the best choice of the test statistic, but it's the traditional one. This is the sample average treatment effect. There are more robust tests to outliers, but I think this is the best one to start to fix ideas. But the question is that in our single randomized experiment, this is the value of the test statistic that we get to observe. But under other realizations of the random assignment mechanism, we could have seen this, or this, or this, or this, and so on. The question is this a large enough value to reject the null hypothesis of no treatment effect? We can answer that question by fixing a significance level, say 5%, the usual level, and just by counting. So what we're going to do here is to sort all the values of the test statistic in decreasing order, and we're going to compute the cumulative probability of observing a test statistic at least at large. So here we can already see that here I have a larger one, and another larger one. If we do this, we see that the observed value of the test statistic has this probability of seeing an alternative value of the test statistic that it's at least at large. This is a randomized experiment in which each pair is randomly assigned to treatment and control with the same probability, 1/32. 1/32 is approximately 3%. Each of these realizations has the same probability. So the cumulative probability of observing a value of the test statistic at least as large as the observed one is a 19%, which under the usual level leads us to reject the null hypothesis of no treatment effect. So we do not have, so here we fail to reject the null hypothesis of no treatment effect. But the point is that for valid inferences about the effect of a treatment in an experiment, it just suffices to require random assignment. Here we have computed the p-values by counting without making any distributional assumptions, and probability here entered the experiment only through random assignment, which was controlled by the experimenter. All right? So I think it's very important to have all these concepts really clear now that we move to an observational study. Because in an observational study, we want to constantly ask ourselves how we would have ideally done that study in the first place. Ideally, we would answer all our causal questions based on a randomized experiment. We cannot afford to do that. We have to live with observational data. But still, we want to ask the question of how I would have done that experiment. If we cannot map our observational study to that ideal randomized experiment, we're often in trouble. Okay? And here, we're going to emphasize methods of adjustment that very closely map the design of an observational study to that randomized experiment we would have done. For this reason, we're going to be using matching, which has pros and cons. It's super transparent, but it comes at some efficiency cost, which I'll describe. All right, so as said, we would ideally run a randomized experiment every time we can, because randomization biases statistical control, namely the law of large numbers ensure that the treatment and control groups are comparable. And second, we can do correct inferences just using random assignment. However, randomization is not always feasible. We cannot always do this, and we have to live with a study that looks like this, where we don't only have a larger reservoir of control units, but they also differ in terms of, for example, here gender. In the control group, we have a larger proportion of females than in the treatment group, and we have to adjust for covariates in some way. But this is one type of biases in observational studies. Biases due to variables that we can see, which we're going to call overt biases. Overt biases are biases that we can take care of by using some form of adjustment, matching, subclassification, regression, which in my mind are all forms of weighting. So overt biases can be taken care of by some form of weighting. Hidden biases are going to be the elephant in the room all the time, and these are biases due to variables that we didn't get to observe. So an overt bias in our running example about the labor training program would be differences in age or education, which we're measuring in our study. Hidden bias would be something like ability. Workers have different abilities, and that also affects their earnings, and it's likely to be correlated with whether they participate or not in the program. And for these biases, we often cannot do match. We can do a sensitivity analysis. We can also come with clever designs. But what I want to emphasize is that this is the difficult part of the problem, hidden biases. So overt biases can be controlled by adjusting for covariates, but hidden biases require other approaches, such as an instrumental variable or a discontinuity in treatment assignment, which under different assumptions, they get us to estimate different estimates to often more local estimates than the sample average treatment effect on the treated. So I wish to discuss a method for adjusting for observed overt biases that is quite transparent. As said, that's matching. And here the motivation is following Cochrane, who coined the term observational studies, is to ask ourselves, when dealing with observational studies, how would the ideal study be conducted if it were possible to do it by control experimentation? All right? So the question is, before introducing the methods, is under what conditions adjusting for observed covariates works? Remember the notation. We have an outcome variable y, a treatment indicator z, and a vector of observed covariates x. Imagine that x includes all the variables that are associated with both the treatment assignment and the potential outcomes. Then if x includes all these relevant covariates, for individuals with a given x, if we're fixing x, if everybody has the same x, the same education, the same age, the same gender, all the relevant confounders, within those cells, those classes defined by x, we have a little randomized experiment. So within values of x, treatment assignment is independent of the potential outcomes under treatment and under control. So in English, what this is saying is the same as before, but within levels of x. This is saying that conditional on all the facts that I can measure about you in a data set, treatment assignment is essentially random. That is the working assumption of most studies in observational studies. This is called the Unconfoundedness Assumption. So again, this assumption is saying that y0 and y1 are conditionally independent of z given x's. And this assumption has many names in different literatures. In econometrics, people speak about this assumption as exogeneity or selection on observables. In statistics, it's often called ignorability, which coupled with the next assumption of positivity is going to be strong ignorability. But this is also related to this notion of missing data, which is missing at random. So we can say that the potential outcomes are missing at random given the observed covariates. So this is going to be perhaps this central assumption that we're going to make. But we also need this assumption. This is often called the positivity or overlap assumption, which says that treatment assignment is not deterministic for all the possible values of x. So for every possible combination of the x's, there's a positive probability of receiving treatment which is different than 1. So for every value of x, you have a positive probability of being treated or controlled. Otherwise, you cannot make inferences about subjects with those levels of x. Under these assumptions, we can see the quantity that we wish to estimate from the observed data. We wish to estimate the average treatment effect on the treated. Again, by linearity of expectations, we can break the expectation of the difference into this difference of expectations. This quantity over here, it's easy because it's directly estimable from the data. Because under treatment, I get to see the potential outcome under treatment. This is just the observed outcome, which I could even compute by taking the sample average. The difficult quantity is this one here, because I'm asking what's the mean of the potential outcomes under control for the treated subjects. And what is going to get us there is going to be the unconfoundedness assumption in addition to using iterated expectations. So by using iterated expectations, we have this expectation over the x's for all the possible values of x's. This is also called the tower property. And then by unconfoundedness, I can change this index here. Because we said that for levels of x, I have a little randomized experiment, like before. And now we're in business, because for the controls, I get to see the potential outcome under control. So this quantity is directly estimable from the data. So we're going to write as follows the mean potential outcome for treatment set given the observed covariates. And under the above assumptions, we can compute this just from the regression on the data, which suggests an estimator of the following form. This suggests an estimator in which we're fitting a regression model on the controls, and then we're averaging the predictions of the potential outcomes under control for the treated subjects. And we can do this, for example, by using linear regression. And what I want to show is that linear regression can go wrong, so we want to use something different. In this example here, we're going to have here in the x-axis the earnings before the labor training program, and in the y-axis the earnings after the program. We're going to suppose that the physical model that generates the outcomes under treatment is a curve like this one. For the controls, by contrast, it's going to be a function like this one. So this is the mean potential outcome function of the outcomes under control, the potential outcomes under control and under treatment for levels of earning. Imagine that in our observed data, we get to see these observations for the treated subjects and these observations for the controls. So overlap is not great. For the control subjects, we get to see people with lower incomes. And for the treated subjects, we get to see people with comparatively larger incomes. Right? The problem with estimating this effect with linear regression is that we're assuming that we have this constant additive treatment effect all the way through. And by specifying these true regression functions here, in this example here, we're going to greatly underestimate the average treatment effect on the treated because we misspecified the model. So we would like to estimate these quantities in a way that we are more robust to model misspecification. That's one thing. In such a way that when there's limited overlap in covariate distributions, I am more robust to that misspecification. We don't want to give an answer about a causal effect where we essentially don't have data, right? we want to restrict our inferences to those portions of the sample where we have both treatment and control observations. This is often going to change our estimate, all right? But there's an argument to be made that it's better to change your estimate and target something for which you have data than for something that for which you're imposing a very strong model. All right? And the other thing is this point that Don Rubin has been making for quite some time, that is that in practice, we want to blind ourselves when doing the statistical adjustments. In a randomized experiment, we never got to see the outcomes until after we did the experiment, right? So we were blinded to see the effectiveness of treatment. In a similar way, in an observational study, there's a case to be made that we want to adjust for covariates without looking at the outcomes. The point is that with routine analysis of linear regression methods, we're simultaneously adjusting for covariates in a way that is not all that transparent, by the way. I can explain that if you wish afterwards. But at the same time, we're seeing what's the coefficient of that treatment indicator, right? So there's this temptation of selecting a model that better suits our hypothesis by including h squared, and h cubed, as opposed to just h, because the findings are better suited to our hypothesis. So what we would like to do is to adjust for covariates in a way that we are approximating this ideal randomized experiment that we would have done without using the outcomes, and in such a way that our estimator is going to be sample bounded, in the sense that we are not extrapolating like we did here with this regression model. And for this, what we're going to do is matching. You could do other things like weighting. We're going to do matching today because of time, and also because it has this nice sensitivity analysis to hidden bias, which is quite transparent, we find. So I think this is a good moment to take a break, to take a 15-minute break, and then we can take it over with matching methods and show you an example on R in sensitivity analysis and others. Thanks. Now better? Yes. Yeah, I said that now the fun part is going to begin. Well, in a randomized experiment, the treatment and control groups are similar in terms of their observed and unobserved covariates. Sadly, in an observational study, which is most of the time, they're not. So we need to adjust for covariates. And perhaps the simplest and most transparent way of adjusting for covariates is by doing pair matching. Like, for example, here, we're trying to find a clone for every treated subject in the control group, right? We're trying to find this randomized experiment that is quote-unquote hidden inside the observational study. That's the intuition behind matching. And we're going to do it exactly in this way by forming pairs first. And this can be relaxed into more general matching structures and a weighting in general. The goal of matching is to find this nice stable 1 for covariate balance. Often an observational study starts by showing, also randomized experiment study, starts by showing there's balance in the treatment and control group. We have a similar distribution, a similar mean, for example, for H in the treatment and the control group, often measured by the standardized difference in means, which is nothing but the difference between these two means over a pooled standard deviation that takes the simple average of the standard deviations, the simple average of the, you take the variance, divide each of the variance by 2 and take the square root of that, this is this. So it's a standardized difference. It's a difference in terms of standard deviations. And we want to find something like this nice stable 1 for covariate balance. So why matching?
I have a question. So the last two variables actually, is that why you want to, is that the outcome variable?
The question is whether these last two variables are outcomes.
The last two variables is that you try to measure earnings.
Yes, the last two variables, the question is whether earnings here are outcomes. No, these are covariates. All these are variables measured before the treatment. Okay. A covariate by definition is going to be something measured before the treatment. We're measuring age, education, race, married, and so on, earnings before the treatment, and then we're asking what is the impact of the labor training program on earnings afterwards, right? So we're going to measure earnings, I believe it's in year 78, but this is before. And if this were a randomized experiment, our table 1 for covariate balance would look something like this. So all the covariates are balanced across treatment groups.
So, my question, let me see whether I understand. So you can both match on X and Y as long as Y is pre-treatment?
Correct.
Oh.
Yeah, the question was whether we can match on lagged outcomes measured before the treatment. The answer is yes. You can think of them as a covariate. And it's actually the ideal thing to do because they're very strong predictors of the outcome afterwards. They're really good covariates most of the time. Thanks. And as a matter of fact, in this particular example, these covariates generated a lot of literature because there are studies without the 75 measure or the 74 measure, and the results are different when you control or not for that covariate. So why matching? First, we would say because of its conceptual simplicity. Here we're making an apples-to-apples comparison where the unit of analysis remains intact. I don't know, Sharon-Lise, after matching remains to be Sharon-Lise as opposed to be a weighted combination of people that represent her, which is also okay, you know, but this facilitates, I think, simpler forms of inference. Also, if I want to collect more information about a given unit in the sample, it's easier to do it this way, and so on. So the unit of analysis remains intact. Second, the adjustments made by matching for covariates are an interpolation based on the available data as opposed to an extrapolation based on a model that can be specified that goes beyond the support of the data. Third, we're going to use matching without using the outcomes, therefore preventing selecting adjustments that better suit our hypothesis. This is the argument about blinding ourselves in matching. And it also facilitates sensitivity analysis to hidden confounders. The sensitivity analysis model that we're going to use to see what would need to be the influence of an unobserved covariate to explain away our effect estimates, I think it's simpler than with other methods. We're going to discuss some matching methods, but I wish to acknowledge there are many other matching methods, namely all this literature on nearest neighbor matching, started, I understand, by Rubin and formalized by Abadi and Invens. Then there's this literature on optimal matching by Rosenbaum and Hansen. Here in the university, Gary King and co-authors have developed coarse and exact matching. We also have genetic matching, the covariate balancing propensity score, matching via network flows. There are many forms of matching. Here today we're going to be using certain optimization tools, namely integer programming tools, in order to balance covariates very well and very closely match individual units. I just want to tell you guys that there are many other methods out there. So when it comes to matching, yes?
Once you've done the matching, are there candidates in either treated or controlled that are not included in the match and therefore discarded?
Yes, the question is whether after matching we're using all the observations that we initially had. In the vast majority of time, the answer is yes, we're dropping observations. And I would argue we want to do that because those other observations are too different. And you can only say something about them based on a model for which perhaps we don't have a very strong justification. Yes? Another side of this question that you're asking is whether I'm using all the treated subjects that I had to begin. I said that my estimate was going to be the sample average treatment effect on the treated. Well, if I drop some treated subjects, my estimate generally is not going to be that one. Okay? It's going to be a more local average treatment effect, the average treatment effect for the matched units.
Depending on scale. Scale of the number of candidates in the cohorts.
Yes, so the feasibility of matching all the observations typically depend on the number of control subjects and treated subjects that you have in the two treatment groups. That yes. But we're going to discuss a technique here which, while dropping treated observations, you can still target the ATT based on covariates. So you're going to find the largest match sample of treatment and control subjects that have a similar covariate structure than the original treated sample. All right? So you can still be discarding subjects, but in a sense, still targeting this parameter for all the treated subjects.
Discarded subjects have an impact on the error bounds or precision of the estimate?
Yes, because the smaller is your sample size. The question is whether the discarded subjects will have an impact on the precision of my effect estimates. Well, the smaller is your match sample, the larger are going to be your standard errors. Yes. So in that sense, yes. All right. Any other questions? Yes. There's a bias-variance trade-off in doing that. Other questions? So we want to adjust for covariates, and ideally we would do this by finding clones, by matching a female with a given age and a given race and a given education in the treatment group to a female with exactly the same covariates. But this is not very practical. If we have one binary covariate, then we have two types of units, as depicted by this tree here. But if we have if we have two binary covariates, now we have four types of units, right? With 3 we have 8, with 4 we have 16, with 5 we have 32 units, and with 20 binary covariates we have over 1 million type of units. So for the typical observational study, where we don't have 20 binary covariates, but we have 20 continuous covariates, or 60 continuous covariates, or hundreds of them, there are just no people on Earth to exactly match exactly for everything. So this is a great impulse, something great that we would ideally do, but we can never do it in practice. What we can do in practice is to balance covariates in aggregate, which is what, after all, randomization is doing. Randomization is buying us this covariate in aggregate, in expectation. So we're going to target that in our observational study, balance in aggregate. And a fundamental tool for doing this is the propensity score, introduced by Rosenbaum and Rubin in a landmark paper in 1983. What is the propensity score? The propensity score denoted there is the conditional probability of receiving treatment given the observed covariates. Not given the unobserved covariates, given the observed covariates. That's the definition of the propensity score. The propensity score is this very helpful dimensionality reduction technique where we can summarize all the X's, P of them, many of them, P can into this single scalar, the propensity score, that has these great properties. Property number 1 is that matching on the propensity score tends to balance all the covariates you use to estimate the score. So by working solely with the propensity score, the promise of the propensity score, and this is a theorem, is that you will tend to balance all the covariates used to estimate the score. That is quite handy, was especially handy like, in the 1980s when this was introduced and computers were not that powerful. So it's a very practical tool, I would say, especially then, now less, but conceptually it's very, very important. And the other property of the propensity score is that it's the coarsest summary of the data. You can balance the P covariates, it suffices to work with this one-dimensional score. Okay? Because of these properties of the propensity score is that it's widely used in practice, the propensity score, often in matching, in weighting, and in regression. When it comes to matching, the way we work with the propensity score is by defining a distance between the propensity score of a given treatment unit T and a control unit C. So if you're treated and you're control, I estimate the propensity score for both of you, and here I compute the absolute value difference between the two of you. And I can imagine doing this for you and the difference and all the people in the control group. So we can imagine building this distance matrix, where we have all the possible pairwise distances between treatment and control subjects. And I could do this in this scale or the logit scale. Alternatively, we can use the propensity score as calipers, as is often used, such that when we're close on a caliper in terms of the propensity score, then the distance is some version of a Mahalanobis distance. Here we have a robust version, which is robust to outliers and to rare binary outcomes. So I don't want to get bogged down in the notation. The point is that this is the Mahalanobis distance when you're close on the covariates. Sorry, when you're close on the propensity score. When you're far on the propensity score, the distance is a very large number, so you prevent two units from being matched. And this is often the distance that is recommended in practice. But this distance doesn't work that great, as I will discuss later, because at the end of the day, we want to balance covariates. The propensity score and the Mahalanobis distance are an instrument to achieve balance. So if it's balance what we care about, why not target it directly? That is the logic of the methods we're going to discuss. Based on the propensity score, we can define these distances that I said here. Now that we have distances between every possible pair of units, we need an algorithm to pair the units. The most widely used algorithm for matching is nearest neighbor matching, which in its most basic form, what it does is to sort all the subjects based on the estimated propensity score. We sort all the treated subjects, for example, in decreasing order. And then for the first subject here in the treatment group, I find the closest control. And I match them with pairs, for example, with or without replacement. If it's without replacement, then I remove these two subjects and I move to the next guy. And so on I go, matching all the subjects. Right? I find the closest available control once at a time, making this first best decision once at a time. Which is an algorithm that is quite handy because in the sense that it's you can run this algorithm very quickly, but it's not optimal. It's not optimal in terms of distances because you're not minimizing the total sum of covariate distances, you're making these one at a time best decisions. So you're not necessarily minimizing the distances. So then there's this literature developed by Paul Rosenbaum, Ben Hansen, and others, where they develop these algorithms for optimal matching, where using most of the time network flow algorithms, they find at once, not making these one at a time decisions, they at once find the optimal configuration of treatment and control subjects that minimizes the total sum of covariate distances. Right? And a version of this problem is the assignment algorithm in the optimization literature. But there are difficulties with both of these approaches. Both of these approaches rely on a summary distance of the covariates, namely the propensity score, which has those two wonderful properties that I mentioned, but these are stochastic properties. They're properties that hold in an appeal to the law of large numbers. What I'm trying to say is that these properties will hold over repeated realizations of the data generating mechanism, but I don't have the guarantee that in my given data set, by optimally matching on the propensity score, I will get good balance. That's the case even if I estimate correctly the propensity score. Because if your covariates are sparse for the size of your data set, then the law of large numbers will not kick in, and you will not necessarily balance the covariates, even if you're estimating correctly the score. And of course, this is more difficult because in practice, we never know that we're estimating correctly the propensity score. So there's a lot of iteration and guesswork when we're trying to balance covariates with distance-driven algorithms for matching. And this makes very difficult balancing the means of the covariates, but we often want to balance more than the means of the covariates. We want to balance the entire distributions of the covariates. Right? So what we're going to do instead is to have a more general matching framework in which we're going to use integer programming to directly target covariate balance. And the matching framework here goes as follows. We're going to solve this optimization problem that has these two components, this objective function here that I'm highlighting, and these constraints here. Our decision variables are going to be this vector of m's, which are going to be assignment indicators. If I match you to you, or you to you. All right? And we're going to minimize this objective function where we have these two terms that compete with each other. We're going to minimize the total sum of distances between match units, for example, using the propensity score distance. And we're going to minimize the negative of the information of the match sample. So if we're minimizing something that is negative, we're maximizing the information. The idea is that we often have to subset the matches. And we want to subset them in such a way that we find the largest subset of the data, in a way that we're maximizing the precision of our estimator. All right? And we're going to do this subject to matching constraints, balancing constraints, and representativeness constraints. The matching constraints are going to enforce a matching structure, like, for example, forming pairs or one-to-many matches, if I want to match with a variable ratio. The balancing constraints are going to balance almost anything that we want, ranging from mean balance to balancing the joint distributions if the data allows us to do that. A relevant question is going to be, what should we be balancing? And we can talk about that too. But in principle, if the data allows us, we could balance anything here. So these constraints can be quite intricate. In practice, we don't have enough observations to balance everything. But you can write the program like this. And we're also going to have these representativeness constraints in such a way that we are not necessarily finding this control group that looks like the treatment group, but we're going to match these two groups towards a reference group or a reference distribution, so that this is representative of a target sample, and under certain assumptions about sampling, representative of the population. So that is the idea. And in this framework here, optimal matching is a particular case where lambda is equals to 0, so we're minimizing distances subject to matching constraints. And another instance of this problem, which we're going to discuss today, is what is called cardinality matching, where you're minimizing the negative of the information of the match sample subject to matching, balancing, and representativeness constraints. If the matching constraints enforce pairs, forming pairs, that is what we're going to do today, then this information is the total number of match pairs. So you're maximizing the total number of match pairs subject to matching, balancing, and representativeness constraints. It's called cardinality matching because it maximizes the cardinality or size of the match sample subject to these constraints. All right? What is this going to bias? Let me show you a pseudo algorithm with distance-driven methods for matching. The way we proceed in practice is first by specifying what constitutes good balance for us. For example, we want to balance the means of the covariates. What we do next is to repeat the following steps. We estimate the propensity score, the Mahalanobis distance, or something else, and with those distances, we often have to trim the observations according to whether they overlap or not based on the estimated propensity score. Then we match on this summary measure, for example, using nearest neighbor matching, and then we assess covariate balance. What happens if balance does not meet the covariate requirements that we have here? We have to repeat. We have to estimate the propensity score using a different functional form, for example, including higher order terms for those covariates that are out of balance, or by modifying the distance matrix by having penalties for a given covariate. But the point is that there can be a lot of iteration here in order to achieve balance. So we repeat this until we find a balanced sample. By contrast with cardinality matching, we're going to have the first the same first step, which is going to be to specify the covariant balance requirements, and then we're going to directly optimize to find the largest match sample that satisfies such requirements. And we're going to be done, because by construction, we're going to get an answer or not. We're directly optimizing towards this. It is true that in this step here, 1, I'm not paying attention to covariant distances. I'm just finding the largest match sample. So this is purely a weighting, a 0-1 weighting, right? But that is not a problem, because after cardinality matching for balance, you have found the largest match sample of, say, 5 match pairs that is balanced relative to the covariates. What I can do next is to repair these subjects in order to minimize covariant distances. And moreover, I can go back to the original data set, and for that fixed size data set that I obtained in step 1, I find the optimal matching in terms of distances that minimize covariant distances, but I will know that it's going to preserve this covariant balance. Okay? Because I'm going to impose those constraints again in that problem. So this procedure dominates optimal matching in terms of distances and covariant and balance for simple matching structures. You're going to get the same covariant distances, but with better covariant balance. All right? So Cochrane, in one of his landmark papers in Causal Inference, gave 2 pieces of advice when designing observational studies. First, he said, when selecting samples for study, make sure that they're large enough to have complete enough data to allow effects of practical importance to be estimated, and avoid treatments and control groups with large initial differences on confounding variables. And he also argued that we should use both the statistician and the subject matter expert knowledge in the planning stages. So this means that the statistician and the doctor have to work together in doing these adjustments. One can argue that cardinality matching is doing this by finding the largest match sample that is balanced, and the subject matter expert knowledge here in the cardinality matching problem comes into the matching problem via the balancing constraints, because he's telling you which ones are the relevant covariates and more or less to what extent you should balance them. So in principle, you can do this. In practice, it's quite difficult to select the covariates and to select to what extent to balance them. I can discuss that more in a second, because we have made some progress along those lines, but a lot more remains to be done. But in principle, you can do something very much in this spirit with cardinality matching. And you can balance anything here, ranging from mean balance to balancing the joint distributions. You can have constraints on exact matching for the groups or the pairs, on an approximation to exact matching that is called near exact matching or almost exact matching, and you can have balance in aggregate for joint distributions and marginal distributions, and there's the room in between when you balance, for example, two-way interactions of covariates. So you balance the joint distributions of pairs of covariates, something that is often called strength K balance, you can implement here. And you can balance moments ranging from means to variances to skewness and so on. So in principle, you can balance many things. And here I would like to give you an example of how to use this. I can share this code with you if after the tutorial. And what I'm going to show is how to implement these things in this package that we wrote with Chinar Kilcioglu and Juan Pablo Bielma called Design Match for R. Okay, can you read well? Yes? Everything is very commented, so if you do this at home, you should be able to understand everything. What we're going to do first is to load the design match library, which has this help file here that says that this is a package for match design in randomized experiments and observational studies. It basically has 2 functions, the function bmatch for bipartite matching and the function nmatch for non-bipartite matching. Bipartite matching is when you have 2 groups that are defined before matching, a treatment and a control group. Non-bipartite matching is when you don't have those labels. For example, when you want to match similar subjects and then randomly assign them to treatment. First you match, then you randomize within match pairs. So for the most, we're going to be using the B-match function in practice, I think. And we have another function called cardmatch, which is an optimized version of B-match for doing cardinality matching. Okay? Let me continue through this example. I'm going to load some auxiliary functions here. And here we have this labor training example, this Lalonde example, which I'm going to attach here to R, and I'm going to briefly describe it. In this data set, we have 185 treated subjects and 429 controls. And in order to estimate the sample average treatment effect, I'm going to find pairs of control subjects that look very much like the treated subjects. These are the variables in the data set. Let me make this bigger so that we can see everything together. These are the same covariates that we had before. All these variables are measured before the treatment. And we can see here the mean of the treated subjects and the control subjects for each of these covariates. And what do we see? How does balance look like? Looks okay? Well, I guess for this covariate here, education, it looks pretty good, right? But for these covariates here, like married and this income variable, it doesn't look great. Oftentimes, the rule of thumb is to say that covariates are balanced when the standardized difference in means in absolute value is smaller than 0.1. And here it's a lot larger than this. Okay? That rule is questionable, but that's the rule people often use in practice, 0.1 standardized difference in means. Yes?
So this brings up a good point. In this case, you might choose a subset of the treated patients in order to achieve your balance, thus discarding your treated patient, some of your treated patients. Is there a way to impose a constraint that you're going to use all of your treated patients because you have a lot more untreated patients to match?
Yes. The question is whether there is a way of imposing a constraint such that I use all the treated subjects. The answer is yes. We're going to do that. Let me show you in a second. Because this data has certain difficulties that also highlight what happens with other methods. So let me explain this in a second. But the answer is yes. You can do that, and we will be doing that. So what we're going to do first is, using all the treated observations, we're going to do optimal matching based on a covariate distance, which here is going to be the Mahalanobis distance, but it could be the propensity score. So for starters, we're going to use something in the domain of nearest neighbor matching, actually optimal matching, such that we find an optimal pair matching that minimizes the total sum of covariate distances between match pairs using the Mahalanobis distance, and we're going to check balance. For this, what I need to do first is to define the treatment indicator, which looks like this, and we need to sort it in decreasing order to not get errors. So we had 185 treated subjects and 429 controls. Then what we're going to do is, using all the covariates that I showed you in this table 1 for covariate balance, is to build this Mahalanobis distance matrix, which I just did with this command here. And this distance matrix is going to have 185 rows for the treated subjects and 429 columns for the controls. So we have all the possible pairwise distances. For example, here, let me show you the first 5 elements. We have that the distance between treated subject 1 and control 186 is 1.23, but between treated subject 1 and now control 187 is 1.35. And what optimal matching is going to do is to find the optimal assignment or pairing of treatment and control subjects such that the overall distances are minimized. What nearest neighbor matching is doing is something that is doing this one at a time. So here for the first subject, I find the closest control, this one here, 189. I drop this from the analysis, if it's without replacement. I move to the next one. Which one is the closest available control? The first one. I drop it, and so on. So you can see that by making this first best decision one at a time, you can easily end up with a solution that is quite bad in terms of the total covariate distances. But we're going to do this at once by solving a version of by solving the assignment problem, actually. This parameter here allows us to drop some of the treated observations. As you were suggesting before here, we're going to match all the treated subjects. So I'm going to force the total number of pairs to be equal to all the treated subjects. I'm not going to drop any treated observations. And now here you have to choose what solver you're going to use. Design Match gives you the option to work with 4 solvers. Some are free and available for everybody, but they're not the most powerful ones. The most powerful one perhaps is Gurobi, which is free for academic users, but not free for people outside academia. So you may have to pay for it, and people are paying for it. So I mean, for using it in this context, it's a super powerful solver. So if you're in academia, good for you because you don't have to pay for it. And here I have specified that I'm going to use Gurobi. I'm going to find an exact solution. That's the approximate equals 0 option. And then I'm giving all these parameters to Bmatch. If you go to the help file of Bmatch, you see there are many options here. Here we're using some of them only. The point is that here you have all these balancing parameters. For example, if you want to balance the moments of the covariates, or like the means, you specify this. If you want to balance a coarsened version of the Kolmogorov-Smirnov statistic to balance the marginal distribution of a continuous covariate, you use this. If you want to do exact matching, you can use this. If you want to do fine balance, which is distributional balance for nominal covariates, you specify that. You have all these options here. And you have also options for doing far matching, which is relevant when you're handling an instrumental variable. All right? So you have those options here. And we're going to solve the matching problem. It says that it's building the matching problem. We're using Gurobi. And we were able to find the match in a few seconds. And here we're going to see how many treated subjects we matched. 185. So we're matching all the treated subjects. What is the total sum of covariate distances? 41.26, and that's the optimal because we're solving an optimization problem. But the really important thing is whether we balance the covariates. And the question is, did we balance them? Some people say so-so because we said that we wanted to balance them up to 0.1 standardized difference in means. Here we have a big imbalance, here we have another imbalance. So we did a good job with some of the covariates, but not for all of them. The point is that we could improve this via distance-driven methods for matching by tuning the distances in some way or another, but that involves a lot of iteration or guesswork, if you want. So what we're going to do here instead is using all the treated observations, we're going to find a pair matching that minimizes the total sum of covariate distances between matched pairs subject to constraints on mean balance. The new thing is this step here, where I'm going to balance all these covariates such that the differences are at most 0.1 standardized difference. You could specify something different, but we're going to do this for the sake of illustration. So everything is the same as before. So I'm going to select this and run it. And we were able to find a solution here. How many treated subjects are we matching? As we required all of them, to your question, 185. And now we're going to check balance. And now here we see that in one step by construction, we got the balance that we wanted, right? And we were also minimizing distances. Yes?
What's the computational power required?
Okay, this is a really good question. The question is about how expensive it is to run this algorithm, like in general. It depends a lot on the solver that you're using. Gurov is really, really powerful. The default in this package is GLPK. That takes a lot more time. If you're going to use GLPK, I suggest here using approximate equals to 1, because we have a rounding algorithm to solve it more quickly. You're not going to get the exact solution that you want, but you're going to get a pretty good one. All right? Anyways, to try to answer the heart of your question, in practice, we have another version of these functions called card match that I'm going to discuss in a second, where we have been able to solve matching problems with distributional constraints for fine balance with hundreds of thousands of observations in a couple of minutes. So in practice, this is super scalable. And it's a lot more scalable than the implementations that I have seen of other matching approaches based on distances. So you can solve problems with 100,000 of observations in a couple of minutes. So to the extent that that is big data, you can do this pretty effectively with this solver.
And as the number of observations goes up, does the computational time go up linearly or exponentially?
Yes, the question is, how does the computational time scales with the number of observations? Depends on the number of constraints that you have. But to be precise, depends on the nature of the constraints that you have. In general, we cannot predict that. These problems are labeled as NP-hard problems, so we don't have a promise that we will be able to solve them in a given time. But in practice, they're super tractable. So for special instances of some of these problems, we have been able to solve that they're polynomially solvable, but not generally. So the answer is, it does not necessarily scale linearly, but in practice it does. It performs really well. Because these labels are two cores. Polynomial and NP-hard problems are two cores of labels. Yes?
So the large difference, covariable is black.
Okay, you catch that. So as I'm saying here, I cheated, right? I found really good balance, but I dropped the difficult covariate, which was this indicator for black, right? The question is, what happens if I include this covariate? So it's great that you picked that up. I cheated and I didn't include this in the balancing constraints. And I did this because I want to show you what happens if you include that covariate. We're going to solve the same problem as before, but now including that covariate. And the answer that we get is error problem infeasible, which may sound like bad news, but I think it's really good news. Why is that? Because if you were doing this with nearest neighbor matching or optimal matching based on the propensity score, you could be searching for a solution forever. And you would never know if there's a solution or not in the data because you're not directly targeting balance. By doing this, we know that that solution is infeasible, and then we know what options that we have. Certainly in this data set, we don't have the option to use all the treated observations and adjust to this extent for the covariates. So what we can do instead is to go and collect more data, which is not very practical. Another option is to relax the balancing constraints. Another option is to subset the treated observations in such a way that we are using as many of the treated observations such that we have balance. By doing this, we're going to be changing the estimate in principle, unless we balance towards the distribution, towards the sample distribution of the original treated subjects, which I'll discuss in a second. Yes?
So before you put a constraint that your standardized errors are very small, and by doing that, it works. And the trick was that you had to drop one of the covariates. Supposing that you don't drop a covariate, is there another cost, is there another trade-off to making that constraint? Or is it simply that sometimes it won't work with all the available covariates?
Yes. So the question is, what is the cost of including this covariate or not? As said before, there's this bias-variance tradeoff. If you want to adjust very well for the covariates, you have to drop some of the observations, and that increases the variance of your estimator, generally speaking. Yes?
Is there a simple way to prioritize the covariates? Make some of them count more in the distance matrix?
Yes. Let me explain something. Here we're balancing covariates via constraints, so they're all equally important. Another possibility is to write this problem in which those constraints are enforced in the objective function, and you can have different weights for them. You can do that. The original formulation of all these methods was like that, in a paper that I can share with you. But selecting those weights is not that meaningful in practice. It's more meaningful, I find, to define constraints based on units that you're kind of familiar, like age, income, and stuff like that, than to define weights when putting them all together in addition to a distance matrix. So the answer is yes, you can. I think this is more practical, though. Yes?
It seems to me if there's some issue with the blacks, in other words, the blacks are more like, there's some difference between the blacks in the treatment and the control group, that this might hint at some issue with this job training vis-a-vis blacks. In other words, it may be a selective bias problem or some other issue like that.
Yes, that's a very good point. And the way I understand your comment is that we want to adjust for that covariate. And I agree. We're going to do it. We definitely have to adjust for it. The point is that this will force us to drop some observations if we want to balance covariates up to that extent. So what we're going to do now is dropping some of the treated observations. We're going to use cardinality matching to find the largest match sample of pairs for which all the covariates are balanced. Again, up to 0.1 standardized difference in means.
Or you could have a wider standardized mean requirement.
Yes, you could also have a larger requirement for that covariate, such that the problem is instead of dropping observations. Yes. But we said that we wanted to balance all the covariates up to this extent. This is what is often done in the literature. Or 0.2 or 0.1. Yeah. And again, both are questionable. And in the context of weighting, there have been some algorithms to optimally select that. We can discuss that later if you want. So everything is the same as before. But now we're going to have this subset equals to 1 for dropping some of the observations. We're going to allow some observations to be dropped. And let's see what we find. So it took a bit longer to run, but here we have an answer. And now we were able to match 120 pairs. So I said that there were 185 treated subjects to begin. In order to meet these requirements, we have to drop 65 observations. So we are reducing the effective sample size to a fair extent. But that is the cost of adjusting for covariates to this extent with these 0-1 weights implied by matching and not extrapolating. Okay? And that's the case because this is the optimization problem for that. And then we can check balance, and here we get the balance that we wanted. Right? Everything is below 0.1. Now the problem is that by doing this, we have changed the estimate. I said that I wanted to target the sample average treatment effect on the treated, but I'm dropping treated observations. A way to still target something like that is by finding the largest match sample that is not only balanced, but is balanced around the original distribution of the treated, dropping them. And that is what we're going to do here. Everything is the same as before, but now we have added this parameter here, targets, which says that I'm going to target the means of the covariates in the treated group before matching. Okay? And note that here, like before, I'm using the function card match, which is what I would recommend you using because this is the one that scales well to large data sets. So let me run this. We got a solution very quickly, and the number of match pairs that we obtain is 99. And we can see that the groups are not only balanced relative to each other in terms of standardized differences, they're smaller than 0.1, but they're similar to this target, which was the distribution of the treated subjects before doing any adjustments. All right? So these are tools that one can use for matching in observational studies. Yes? All right, the question is, how does this choice of balancing up to 0.1 standardized difference in means affect the standard errors of the effects? This is a really good question. To my knowledge, it's a pretty much open question. So let me tell you what I know about that question. Well, the better you balance the covariates, the more variable are going to be your weights. In this context here, the smaller is going to be your effective sample size. So the better you balance the covariates, the smaller is your bias, but the greater is going to be the variance of your estimator, right? In the context of weighting, we have devised an algorithm for selecting that parameter by making the observation that by balancing covariates, what you're implicitly doing is to model the inverse propensity score function. So that's the key connection. Because once we realize that, we can say that if I'm balancing covariates correctly, then I'm estimating correctly the inverse propensity score function. And if that propensity score function is well specified, I'm going to obtain balance at the population level, in other words, at the sample level, and at the level of samples from that population, in other words, at the level of bootstrap samples from the original sample. So we have a bootstrap procedure where for a grid of values of delta, the imbalance, we choose the level of imbalance that better generalizes to bootstrap samples. That's one answer that we have devised to select this parameter in the context of weighting. In the context of matching, the mode of inference is different, and with Zach Branson, we're thinking about some things along those lines, using a sensitivity analysis to select that. So I think it's a great question. I tend to think that question also applies to experiments. To what extent should you re-randomize such that you say you're happy with that level of balance? So I think it's a really good question, and that's what I know about it. So I think that in practice, people are going to be happy seeing something like 0.1 standardized differences, but it's a good question. And let me say, by the way, that that's also a question that applies to linear regression. Because when you're doing linear regression, you're implicitly weighting the observations. And the question is, how are you implicitly weighting them? And that is not all that clear. But the answer is that you're perfectly balancing the covariates you're including in the model. And if you're doing that, you're making a choice about delta. Delta is equals to 0. Is that the optimal choice? I don't think so, because there's a bias-variance trade-off there again. So I'm just saying that the question you're posing is a very general one that applies to other methods, not only to matching in the context of observational studies. Yes?
You want to use matching to best mimic real life, but you introduce constraints to make sure you have appropriate matches, right? So then you're concerned by dropping out a certain number of your treated samples that you're actually missing something important. They don't match for an important reason. So would it be valid to then treat those ones that dropped out under these conditions as a averaged, I forget what you called it before, but an average model of a person, and use that averaging model with the matching that you're doing here to get the full view of the treated population?
Yeah, if I understand correctly the question is to what extent can we use the unmatched subjects to learn something about treatment effects? That's a good general question. And I guess I would say that under the assumptions of unconfoundedness and overlap we have posed here, this is a valid effect estimate. Those assumptions can be violated, and I guess you're right that we could use them, those controls, in some creative way to learn something else. But we have dropped them because they're different in terms of observed covariates. So I'm just saying that you will be able to use them imposing some strong structure on the data. So I would imagine you could come up with something, but making strong assumptions. Thanks. Yes?
I mean, like, so instead of like drop some observations totally, so is it right that we can use some like kernel-based method, trying to impose some kernel structure and
Yes, the question is whether instead of using the 0-1 weighting for selecting the observations, you can use something like kernels and differentially weight the observations. The answer is yes. People have done things along those lines, specifically in the econometrics literature, to my knowledge. So you could do something like that. The reason I prefer to do something like this is because of the transparency of the adjustments. If I'm going to do matching, I'm going to do a 1-to-1 pair matching, but as soon as I depart from that structure, my take is to go all the way and do a weighting. What you're suggesting is somewhere in between. And it may have advantages to be somewhere in between, but it's not evident to me what are those advantages. Maybe it's something along the lines of applying the synthetic control method to every subject in the other group, and then have a synthetic control for all the subjects. So I can see that could get you something along those lines, but it's not evident to me. The reason we're doing this is because of its transparency, the mode of inference, the sensitivity analysis, these apples-to-apples comparisons where you are in the match sample and not a kernel-weighted version of you. But you could, definitely, and people have had great proposals of that. All right. So I'll share with this code with you if you want, guys. Oh, I'm moving in the other direction now. Okay, what I wish to emphasize that matching can be viewed as a form of weighting where the weights are these 0-1 weights that encode an assignment between units. So units are not only selected, but this assignment between units is explicitly used in inference for match pairs here. On one side of the spectrum, I would say there's matching, which emphasizes study design and interpretability. And at the other side of the spectrum, I would say there's weighting, which emphasizes statistical efficiency and computational tractability. Yeah, those algorithms are a lot more tractable than the ones we're using here, even though we can handle large data sets, as I said before. And certainly, these matching methods can be complemented, can be supplemented or assisted with regression models in the spirit of W robust estimators. So you can use matching and regression if you want. It's not like one or the other. You can think of matching as this design step of your observational study, and then you can do anything you want in principle. You can do simple differences in means, or fit your favorite machine learning method and do something along the lines of G-computation. You could do that. Just be careful on how you compute the standard errors and so on. But there's nothing algorithmically that stops you from doing something like that. So a generalization of this matching procedure that I described are these balancing weights, whereby instead of maximizing the size of the match sample or maximizing the precision of your estimator, here you're minimizing a measure of dispersion of the weights, say the variance, which has a direct impact on the variance of your estimator, subject to balancing constraints that I'm showing here, where we're saying that that the weighted average in, say, the control group has to be similar to this target that you are trying to make inferences about up to a level delta. Okay? I'm just highlighting that the matching problem can be generalized to a weighting problem, where we often do inference in a superpopulation sense. And there are many proposals along these lines, like the work by Hein-Muller, Imai and Radkovich, Chan and others, Fan and others. There are also the balancing weights by, which I forgot to mention here, by Fan Lee, Alex Zaslavsky, and Carrie Locke Morgan. So there are many proposals along these lines. Okay? A generalization of matching as weighting. You're relaxing the weights to vary freely between 0 and 1 in order to increase efficiency. That's the idea. Now, the reason we're doing matching is because of the transparency of its adjustments, the mode of inference, and that we can do a simpler sensitivity analysis to hidden bias. The elephant in the room. You have adjusted for some things, but you didn't adjust for everything. The question is, what can we say about that hidden confounder? So here I'm going to present one mode for sensitivity analysis for match pairs. There are others. What I like about this one is that I think it's very simple, elegant, with few knobs, and quite interpretable. So the question is, can anything more be said about an observational study beyond association is not causation? Can we make this qualitative statement a quantitative one and put a number to that? So a sensitivity analysis is going to be a specific statement about the magnitude of hidden bias that would need to take place in order to explain away our significant findings, right? How large would need to be the influence of a covariate we did not adjust for in the matching to explain away the significant effect estimate? If my results need a very large hidden bias to explain away my estimates, I'm going to say that my study is quite insensitive. Otherwise, if I need a very small bias, it's going to be quite sensitive, very shaky, my results. Only a small bias can explain away what I found. So weak associations in small studies can be explained away by very small biases, but only a very large bias can explain a strong association in a large study. And the model is going to go as follows. So we're going to say that a study is free of hidden bias if the probability of a given unit J of receiving treatment is a function of the observed covariates, period. Alternatively, we're going to say that there's hidden bias is for if two units with the same X's vary in their probability of receiving treatment because of an unobserved covariate U. And in this sensitivity analysis, we're going to ask, how would my inferences about treatment assignment change for hidden biases of different magnitudes? Okay? So we're going to suppose that units with the same X's differ in their probabilities of receiving treatments. How large would need to be these differences to change the conclusions of my studies, moving a significant effect estimate to an insignificant one? So qualitatively changing the conclusions of my study. For this, we're going to assume that in our matches, two units that are matched for their observed covariates, they have the same covariate values, and may differ in their probability of receiving treatment. So they must be differing because of something I didn't account in the matching. And now we're going to write the odds ratios of these two units for receiving treatment. The odds in themselves are a ratio. The odds ratio is a ratio of ratios. So we're writing here these odds ratios for the probability of two units J and K, which were exactly matched on their covariates. We're going to say that they can differ at most by a factor of gamma, and also bounded here by 1 over gamma, right? So if gamma is equals to 1, these pi's are equal, they collapse to pi equals to 1/2. Both units in this match pair had the same probability of receiving treatment. As gamma becomes larger, these probabilities can depart more and more from each other, right? The question is, at what critical value of gamma I cross the line and a significant estimate ceases to be statistically significant. So our results are going to be robust to hidden biases if it takes a very big gamma to explain away my significant effect estimate. So if gamma is equals to 1, then the study is free of hidden bias, and for gamma greater than 1, there is hidden bias. So gamma is a measure of the degree of departure of a study that is free of hidden bias. Let me show you this in the context of the labor training example. I also have code for this that I will share with you. But in our labor training example, we find the largest pair match sample that is balanced relative to the original treatment group. I showed you balance, and balance look okay, right? Then we look at the outcomes. What is the point estimate that we obtain? It's $1,886, which is significant at the 5% level. So labor training increased the earnings of people in the treatment group by that amount. When I adjusted for those like roughly 9 covariates, remember I had age, education, race, the income before the treatment, and so on. The question is that I didn't adjust for everything. I didn't adjust for ability, for example. The question is how large will need to be the influence of that hidden covariate, ability, to explain away this association, right? And the answer is quantified here by this parameter gamma. When gamma is equals to 1, I have 2 extreme case p-values, which are the same, 0.19 as before. But as units depart in their probabilities of being treated because of an unobserved covariate, my extreme case p-values, my worst case analysis, start to depart from each other. This p-value is smaller than this one is larger than this one. As I increase gamma a little bit. As I increase a bit more, this gap becomes larger, and so on. And so I increase gamma up to 0.1, and here I'm at the edge of still being statistically significant, right? But when gamma is equals to 1.11, then my worst case analysis ceases to be statistically significant. So how robust are my findings to hidden biases? In this example, not all that robust. Because 2 units that are exactly matched for all their observed covariates would need to depart in their odds of receiving treatment by only a factor of 1.11, which is not very large. You can compare this to other studies. So for example, in this famous study by Hammond about smoking and lung cancer, if you apply a sensitivity analysis to that study, then the gamma you obtain, and this is a really important study, which basically, it was very convincing to show this association between smoking and lung cancer. That study ceases to be statistically significant at a gamma of something like 5, if I remember correctly. So units that are exactly matched for their observed covariates will need to be different because of in their odds of receiving treatment because of an unobserved covariate, by this unobserved covariate that changes their odds by a factor of 5. So this forces you to put a name to that unobserved covariate and see whether that can explain that level of departure. In this case here, yeah, the results are not that sensitive, but we have this that robust, I'm saying. They're quite sensitive. But the point is that we have this additional layer on the statistical analysis, which to some extent, under a model for sure, quantifies the extent that that hidden covariate would need to play in the analysis to explain away your significant estimates. Yes?
Covariants are unobserved. How do you compute gamma?
Yeah, the question is, if the covariates are unobserved, how do you compute gamma? The way it goes is as follows. For different values of gamma that you give me, I compute the extreme case p-values. And the value of gamma, the critical one is the one your findings cease to be statistically significant for both cases. So you're not computing gamma. You give me gamma, and I give you the extreme cases of the p-value.
But the covariant is unobserved. How do you know what you're looking for?
Well, this unobserved covariate, it's a worst case analysis. And for that worst case analysis, you can compute the value of the test statistic here and here.
So it's an estimate
And
of robustness.
I guess you can think about it in that way. Yes?
In this context, this would be perhaps a measure of how much creaming the people, how much the people who ran the program tried to select people who they thought would benefit most from it.
So they have ideas of those unobserved variables.
That's right, that they had some sense
And
of.
they just want to make an estimate of robustness.
Yeah.
Yes.
Given that you have, I don't know, 100 different choices you could easily make to set this up in terms of different constraints and different methods and so forth, would you view this gamma method as a way to say, like, my method that I happen to have chosen is pretty decent because gamma is big, or is that too strong of a statement?
That is really a great question. That's great intuition. The question is, in your matching framework, you have all these decisions you can make. You can balance covariates to different extent, and so on. There are many choices you have. The question is, to what extent can you use this sensitivity parameter gamma to choose a match design? And that's exactly what we're doing with Zach Branson to select how closely to balance the covariates. We're going to choose the degree of adjustment such that the power of a sensitivity analysis as high as possible. So I think that's great intuition. All right. This sensitivity analysis is in the spirit of this first sensitivity analysis developed by Cornfield, but there are other approaches to sensitivity analysis, including these ones here. There's a quite different one by Rosenbaum and Rubin. Robbins has another very nice one. Invens, then here's a Bayesian one by McCandless and co-authors, and Vanderwill and Ding recently proposed the E-value. There are extensions of this sensitivity analysis to weak nulls, and there's a very nice paper by Colin Fogarty on this forthcoming in JASA. And all these sensitivity analysis methods that we have discussed today are implemented in these 2 R packages by Paul Rosenbaum, which you can download through CRAN. All right. In the slides, you will see some discussion about other approaches to control for unobserved variation, namely using instrumental variables and discontinuity designs. Today, in the interest of time, I'm going to jump to this example to show you how you can generalize these matching tools to work with multi-value treatments and target a representative sample of a population. All right? So here I'm going to switch examples. We're going to forget about the labor training example, and we're going to ask what was the impact of the 2010 Chilean earthquake on educational outcomes. The 2010 Chilean earthquake was a massive earthquake, the 4th strongest earthquake in the world until that time. And yeah, it caused a huge devastation in the country. And the question we're going to ask is, what was the impact of the earthquake on educational achievement? To be more precise, in Chile, to get into college, you have to take a test, period. It's like if you take the SATs, but that's all. Based on the scores that you have in the SAT, you make it to college 1, 2, 3, and so forth. Other things don't come into account. It's purely the test the score that you're getting in that test. So it's a pretty high stakes test. I remember that day being very nervous because depending on the outcome of those 3 days of tests, I was going to make it to one college or the others. So it's quite an event. And in Chile also, higher education is super important. Chile has a super unequal income distribution, and college is one of the main avenues of social mobility. Chile is hit by an earthquake very often because Chile is located on top of these 2 Nazca plates, so we get earthquakes very often. So I think it's natural to ask, what was the impact of the earthquake on educational achievement? And what we're going to do for this is use an administrative census of the same students measured before and after the earthquake. When I say it's an administrative census, I mean that we have all the test scores of the students in a test before the earthquake, and then I also have it after the earthquake to get into college. In baseline, in this administrative data set, we have a very rich set of covariates, like the attendance of the students to school, these test scores before the earthquake, their GPA, school characteristics, socioeconomic characteristics of the student. We have the income of the parents, the education of the parents. We have a very rich set of covariates for which to adjust for. And then we're going to look at two outcomes. We're going to look at the outcomes after the earthquake on school attendance of that last year of school before taking the SAT, and the equivalent of the SAT score. Right? We're going to look at two pairs of outcomes. And the way we're going to design the study is as follows. Here we have a map of Chile, showing here with the black asterisk where the epicenter of the earthquake was. And with all these circles here, I'm showing you the counties where we have data before and after the earthquake. And we're coloring these circles here with the strength of the earthquake, the peak ground acceleration of the earthquake. So very close to the epicenter, there was very strong shaking, and closer to the extreme of the countries, the people barely felt the earthquake. So based on these levels of shaking, we're going to think of doses of treatment, levels of exposure to the treatment. And we're going to define 3, 5, and 10 levels of exposure to the treatment based on basically terciles, quintiles, and deciles of exposures to the earthquake. And we're going to build this study that attempts to replicate this randomized experiment, that it's as if people were randomly assigned to live in different parts of the country, given their observed covariates. That is the study we're trying to approximate here. And one way to do this would be by matching on the propensity score, or to be precise, a generalization of the propensity score for multi-value treatments. But if balancing covariates was difficult for binary treatments, now with multi-value treatments it's even more difficult. Even checking balance is difficult with multi-value treatments. And we also want to analyze the outcomes in a very simple and structured way. Oftentimes with these methods, you have to fit more complex models to analyze the outcomes. And we would like to be able to show plots and tables and figures to see what is going on with the effects. So we're going to use matching for this. We're going to match in a different way. And for this, we're going to use the idea of template matching, which I'm going to describe in a second. Conventionally, when we do matching, we try to match all the treated subjects to similar controls, right? When the treatment group is different than the control group, so here we have run out of rectangles, we cannot afford to match all the treated subjects, right? We drop some of the treated subjects. We're matching a subset of the treated subjects. And by doing this, we're changing the estimand. But we would still like to target something that looked like the original sample, or the original population, if you want to post a population sampling model too. And what we're going to do here is to slightly extend this idea of template matching by Jeff Silver, Paul Rosenbaum, and co-authors, where they proposed to use matching with the previous tools that I described to do hospital comparisons. So they wanted to do a fair comparison of hospitals by comparing the same case mixes of patients across all hospitals. We know that different hospitals tend to treat different kind of patients. Some hospitals get sicker patients, others not. So in order to do a fair comparison, we have to make an apples-to-apples comparison. And they try to do matching, but if you are going to match with many hospitals, if H is very large, matching in this direction is a nightmare. But they were very clever to think, okay, what if I define an auxiliary sample, a target sample, and I match each of these groups to that template? Then by virtue of doing that, I'm going to get a match across all hospitals. So I think it's a really important idea, which we can slightly extend to the context of representative matching with doses by selecting that template sample to be a random sample from a target population. By being a random sample, it's going to be representative of a target population. And there's also a way that we can make it be the best random sample from a target population by selecting many random samples and choosing the closest random sample to this one here. It's still random, but it's the best one. And now what we're going to do is to match across doses in this direction here. And by doing this, we can balance covariates very precisely. Here I'm showing you a table 1 for covariate balance, but that it's a lot more precise than a table 1 for covariate balance, because we're not only balancing the means of the covariates, we're perfectly balancing the marginal distributions of the covariates. For example, gender here. Across all the levels of shaking of the earthquake, we have the same number of counts of males and females. We have the same number of students in low school socioeconomic status schools, right? Every category of every covariate, and we have like 17 of them, so this is a very long table, is perfectly represented across all the doses. So we're not only perfectly balancing the means, we're perfectly balancing the distributions. And this is something that you can do by using the previous matching tool. So I think one can make a strong case that the groups are comparable in terms of observed covariates. And I find this handy, this kind of adjustment, because then we can analyze the outcomes by simply looking at them. We can simply plot the outcomes. I told you there are two outcomes. One outcome is school attendance. The other were the PSU scores, similar to the SAT scores. And let's focus on this panel here. Here we have the distributions of difference in attendance between those two and the baseline dose 1. And we essentially see no effect. This box plot is centered around 0. When I take that difference, for example, between dose 6 and dose 1, everything is in relation to dose 1 here, this effect now is larger. And we can see that the stronger is the shaking of the earthquake, the bigger is the effect. So we see this dose-response relationship of the impact of the shaking of the earthquake on whether students, to what extent students attended to school after the earthquake. It is not surprising to find this, but the point I want to make is that we're seeing these effects, and it's very transparent what we're doing with the data. Here you can see how we're adjusting for covariates. So we can simply plot the outcomes. The point is that we can do something similar for the PSU scores, and here's what we see. So let's focus on this panel here again. This is what we had before, and this is what we have now. And what do we see? We see nothing, right? Which is quite striking, because the earthquake has this massive effect on so many things in Chile, including school attendance. But when it comes to take the PSU test to get into college, it appears it didn't have an effect. Which is interesting, as you say, and also controversial, one may say. Like one hypothesis, a corrosive hypothesis, is what are students really learning in the last year of school towards this test? Maybe it's the case that they're learning everything outside school, so going to school is not all that relevant.
Well, just the top 10%. You only lose a little bit of attendance in your previous slide. So just that small percentage of people that drop in attendance, those are the ones that didn't need to go to class anyway.
That's a possibility, but the point I wish to highlight is that here we're using matching to handle many treatment doses, 10 of them. The adjustments are transparent. You saw the tables for balance, and then we can look at the outcomes. And so the point is that it facilitates, I think, transparent analysis of the outcomes and transparent sensitivity analysis too. Yes?
What's the time difference between the PSU exam and the earthquakes?
Oh, the question is, what was the time difference between the earthquake and the PSU? I think it was roughly something like 9 months in this case. Yes?
What was the cost in N?
The cost in N?
Yeah, what was your final match population divided by the total?
Yes, so here for every treatment dose, we have a match sample of size 1,000 because we're doing it, the template I chose it to be of size 1,000. But you can optimize that too so that it's much larger. This is just for the sake of illustration. So it was size 1,000. Each of the samples is size 1,000. And I think here I should finish so that...
Keep finishing. You just keep going to the practical. Yeah.
Oh, but...
You go ahead.
To the practical part? Okay. So we have emphasized certain study design principles here, which we think there are some important study design principles regardless of whether we use matching or something else, right? If you're going to use a different method for adjustment, we still think it's really important to be careful about design, to specify what is the target population and your estimate, under what assumptions can you get to see that estimate from the observed data, and to avoid strong parametric specifications. And I think it's important that these adjustments are transparent in the sense that we know what we are doing to the data, what differential weighting we're doing to the data. With linear regression, as it turns out, as Hiro Invens has explained in one of his papers, the implied weights can be very large and negative, which can translate into a lot of extrapolation. So matching maps these principles in the sense, it's design based in the sense that we're not using the outcomes. In a way, we're focusing on the treatment assignment mechanism. We adhering to this concept of target population by doing template matching. What are the assumptions are stated here. The parametric specifications, it's tempting to say they're virtually none, but from the moment we are targeting certain forms of covariate balance, if we don't have a non-parametric agenda for balancing things, the justification for balancing some things and not others comes from a parametric family of models. So nearest neighbor matching in principle is non-parametric. You can also do non-parametric balancing, but if you're just balancing the means, that implies a linear model in the end. Okay? So matching is matching can be non-parametric if you do it in that way. And I hope that I have conveyed that the adjustments are transparent. You can see what is going on. Perhaps the algorithms are complex, but at the end of the day, the structure of the data is simple, so that we can talk about the methods. Let me say again that matching is not the silver bullet for the problem of causal inference. It has some very nice appealing characteristics. Again, to repeat, I would think transparency, but we're doing this 0-1 weighting on the data, and a more efficient way of weighting the data would be to relax that weighting, for example. There have been all these advancements in machine learning, which I think they're very valuable, and they can be used, for example, as a complement to matching, or as an alternative to matching. So we wish to emphasize these matching tools because I think they should be part of the toolkit of any one of us doing causal inference in this big data era, and to kind of to remember these design principles from randomized experiments. So in big data, I think we also want to be thinking carefully about this study design considerations, and matching, I think, lends quite naturally to be careful about that thinking. But there are many other methods. So let's finish here. I think we're on time.